All right, it's a pleasure to introduce our first speaker, Yinyu Ye.
Yeah.
Yinyu Ye certainly needs no introduction. He's done a lot of amazing work in optimization and in planning, and today he's going to be talking about some of his new work in this space.
Yeah. Okay. Thank you, Sean. Thanks to the organizer. And so what I'm going to talk about is some kind of related to online linear programming. So many people, I have been working on linear programming since I joined Stanford. So I'm just continue working on this subject. So what I'm outline, I'm going to introduce you what's the online linear programming. So linear programming probably everybody knows. Then I talk about the early and the result on some kind of a competitive ratio. And basically it's the online versus offline. Then I'm going to introduce some new work, which is put some stochastic element over there. Talk about the price convergence. Then we use bound regret and establish some bound on basically on the learning qualities. Then I'm going to talk about the adaptive online linear programming algorithms, and just summary, okay? Basically, the whole idea is develop tractable and also provable models and algorithms for optimization with online or streamlined data. Okay. So introduction. So since I'm from the management science from business side, so I'm going to give a toy example which is related to revenue management, okay, or combinatorial auction. So you can imagine there was a store, sell number of goods, or allocate some resources. There was a fixed selling period, horizon, and a number of buyers. Okay, there was fixed inventory and the goods resource given at the beginning. So you know that. And the customer bidders coming and also require a bundle of goods, resources, and bid with certain prices or rewards. Okay, so the decision is to sell or not to each individual customer or whatever. The objective is still maximize the revenue. Okay, so many applications you can think this is the general online kind of advertising, auction market, packing, routing, revenue, and which we named as resource allocation. So many people know when George Dantzig invented the linear program, they declared that this is a resource allocation programming. So here's the toy example. So we have given inventory for certain goods. Okay, then we have bidders come in. Okay, so this one say I want one pants, I want one shoes, I want one hat, and I'm going to pay for $100. Okay, so second bidder come in. They said, oh no, I'm only interested in the T-shirt and hat. I'm going to willing to pay for $30. So the information is given. So this is the like a basket compilation, which one you want. Okay, if you put 0, you don't want, then this is the information I'm going to bid. Okay, so this is so the question is, and you as a sellers, so you want to decide whether this should be equal to 1. That means sell to these guys, okay, or x equal to 0, basically reject this bid. Okay, so this one, which is once you collect all the information, so this is how many resources, how many goods to allocate, then you choose which one to give, which one is not. Okay, so you still want to maximize this times this, which is the total revenue. Okay, so this is just a linear, or maybe some people call it the 0-1 integer linear programming problems. So you want to decide x, rj, that's the reward, that's the bit values. So aij, that's the 1, 0, or 1. So once you give to this guy, and then you sum it up, so this is the total consumption of a resource I, so this has to be less than bi. Is that clear? Okay. So this is the linear programming. Sometimes we just relax this to be 0, 1. So this is a typical like a packing and linear programming problems. Now we consider the online or streamline and a data-driven version of the problem. We only know B, which is how many inventory available. We have a rough idea how many customers will come during these seasons. That's all we know. Okay. But however, the bit of information, the requirement, and is revealed sequentially, okay, along with the corresponding objective coefficient Rj. So each of these you view as the jth column, and they only come sequentially. And you have to make a revocable decision, must be made, okay, as soon as the order rises without observing the future data. So this is a problem which we call the online linear programming, okay. Instead, wait until all the data revealed. We solve a single static linear programming problems. Then we have to decide on the fly, okay, when data information is revealed. So this problem analyzed, and in the past about 10 years, okay. So this is assumptions. Of course, Aij could be any number between 0 and 1, okay. Rj is greater than 0. And each bit arrive in some kind of rundown orders, okay? So if you solve a static linear program, it really doesn't matter which one is called x1, which order is second order, so you decide altogether. However, for this online, then it really depends on the order revealed. But here we make assumption the buyer pool, the bit pool is already there, but they just revealed in a rundown order, okay? So here's the competitive ratio. So offline LP, we developed by OPT, A, and R. So it all depends on these data, okay? So keep in mind, B is fixed, okay? We call a long line algorithm or policy to be C competitive if and only if whatever rules, whatever position, a policy we decide xj, and that revenue add up over all the possible permutations is greater or equal to C times the offline optimal values. Okay? So any online revenues cannot beat offlines because you can wait and see and then decide. Okay? So we want C to be as close to 1 as possible. Is that? We want this to be true for all the A and R. So it's like a robust. Okay? So then, in what follows, I'm going to let, among all the resource inventories, I'll put B min as the smallest one. Okay. So because the data, so A is already there, decided, they just revealed sequentially. So I have to make sequential decisions, okay, such that expect all the possible orders is greater than C times OPT. Okay. So there was an impossibility result. So for any fixed epsilon, there was no online algorithm for solving the linear program. Online linear program when we decide sequentially online, such that competitive ratio is 1 minus epsilon if B min is less than log m divided by epsilon squared. M is the number of goods. Okay. Okay. So this is impossible to beat because we basically construct a worst case example. It doesn't matter how you manipulate the, which one divided 1, which one is 0. You always have an error if this one bigger than 1 minus epsilon, if B min is not. Okay. And we also have a possibility result. And the worst 1 epsilon competitive online if B min is greater than m log n divided. So if you ignore this kind of and log factors, so this is m divided by epsilon squared. So we can design such algorithms, competitive ratio. It is 1 minus epsilon. This is epsilon squared is the typical statistical bound because there's some kind of random permutation involved over here. Okay. So this is, we write the paper 2010 and some conference and then finally publish it. This joint work with Agrava, Zizor, and a couple of my former students. Whatever. So what's the key idea? How this related to learning? Because that's the theme of this workshop. In turnout, we basically wanted to learn what's the so-called ideal prices. So if I do have itemized ideal price, for example, this is a $45 each, this is the $45 each for a pair of shoes, then the online decision would be very easy. So, for example, if you decide x1 equal to 0, or 1. All you need to see is they want one pair of shoes, that's $90, plus one hat, that's $15. So that's the total $105. His bid price is only 100. That's below the threshold price. So then XGA equal to 0. Okay? In this case, X2, when this one, we take our cost, ideal cost, and itemize the 15, 25. He bid for $30. Then we say yes, and we want to sell to you. Okay? Is that clear? Okay. So the question is, such ideal prices, if you put this as a price policy, can use that price as a benchmark? Can you make these sequential decisions? Sequential decision would be easy, okay? You really don't need to know the futures. All you need to just take the prices. Can you still prove the online revenue still close to offline level? Well, it turned out such a price exists, okay? So that's basically the shadow price of this linear programming. Basically, is the shadow price. You relax this, you put a shadow price, you compute it, use that price as a shadow price. So shadow price, or like a do of this linear programming, become very aggregate, very accurate, and can itemize the things to make sequential decisions. So now the question becomes, how can you quickly learn this shadow price? Okay, so this become a learning problems. Okay, so yeah, the decision, once you have a price, then you equal to 1. If this is greater than this, what you buy, what you bid is greater than the cost. You can think about this, the cost. Otherwise, you go to zeros. Okay, so then, of course, we don't know the data. Compute the true universal shadow price. Need all the data. So what you do is, by learning threshold values sequentially, basically eventual price. So the one algorithm, most algorithm developed so far is we divide this n, so like the epsilon is the tiny percent of orders. I usually set the price very high. So I don't sell to anybody. I just observe the data. Once you have about the epsilon proportion of the customer reviewed the data, then I solve a linear programming problems, okay, with the same proportional resource give to that group. Okay. Another one is called dynamic learning algorithms. So you dynamic update, so you solve this, then use that price as a decision rule. Then after a while, then you update the price because the customer data reviewed more and more as you go. Okay. So this is a chosen period. So specifically, we updated the price at a time with this kind of order power rules. So basically, we choose epsilon n to epsilon for epsilon until 2 epsilon until this k is more than n. Okay, so we solve this linear programming problem. For example, think about that's epsilon equal to 1%. We have 1% customers. Then I give 1% resource to that guy. I solve that linear programming problems. Okay, so and the t divided by n. This group, this epsilon 1%, we give them 1% resource. And here I put a little bit number because we have to, to kill some kind of variance because this is a constrained learning in the decision cannot violate the constraints on one side. Okay, so this is what use a learning rule and linear program. Basically, we solve this proportional data. We give this same proportional resource, pretend this is our LP, we compute the shadow price, use that shadow price as a decision rule for the next until we get 2 epsilon n, then we have a 2 epsilon, we have a large sample size now, we solve a little bit larger linear programming, we compute the shadow price, use that price rule as the second period. Is that clear? Okay, we just sequentially and do this until it's over, okay? So that's the sense, okay? So there was a literature, actually for m equal to 1, it has been studied, and then m greater equal to 1 over m squared. This just, for m equal to 1, this is called the secretary problems or something, whatever, so you already. David Law said, oh, if offline objective is very big, m squared, epsilon, this is a one-time learning, okay? And there was some paper further request, still one time or plus something at some conditions. So this is the paper I talk about. This is the tackle a general packing linear programming. So we only need a mean m log n epsilon square, or it's not n, and or m square log n will lead to objective value. So the idea is basically say, for this online optimization doing well, you have to accumulate enough inventory, okay, such that the learning cost, you have to have some loss at the beginning, so that loss can be made up in the futures. So if your inventory is very, very small, and if you sell jewelry on the online, that's not a good idea because you only feel and you're running out of stock. Okay. So, okay, and then some people improved. The last three papers actually proved even more dynamic linear updating, the b mean less log m divided by epsilon square. But remember, we have an impossibility result, which is if this number is less than that, so you cannot have online algorithms. So in that case, and this kind of rule become optimal. Okay? So lower bound is log m divided by epsilon square, and also the upper bound or sufficient condition to develop 1 minus epsilon competitive is also log m divided by epsilon square. Okay, epsilon square. So this is some kind of early result. But here, we still have some questions at the time. Does the dual price vector converge? Does the price have a concentration? Okay. Although right now we just analyze the revenue, but we don't care whether the price convergence or not. As long as this price give a reasonable revenue, which is one scalar. But here, if price is the m itemized and price, whatever. Okay. Can we dealing with buy and sell model? Remember, on this problem, everybody here, they just make a buy-in. Can we also allow some of this coefficient to be lactive? What I mean, RG and AIG have some lactive entries. So that means the seller actually also buys something back. Okay? So in that case, this becomes a true linear programming problems. If all require all linear programming, every coefficient to be non-active, this is the one-sided market, and we call it the packing linear programming. So when we submit a paper, we call it online linear programming. Some phrase says, oh, this is not true linear programming, because linear programming, the coefficient can be both positive and negative. It's really double market. Whatever. Okay. Can we have a very good regret? So right now, we just fixed n. We just analyze with respect to epsilon. What about as a increase? Does this error how increase? Okay, possible. So this is typically called a regret. Regret measure are popularly used in statistical, economic, operation research. So, okay. Also, online algorithm depend not only on the reviewed data, but also on the action of decision already made. So if you take a look at my linear programming problems, okay, so one depend on reviewed data and it's a proportional resource give to that number of customers. We ignored all the decision already made, okay? So in that case, we call this is open loop kind of learning, whatever. So people here money in the control, and you have an open loop, and then you have a closed loop. So what we're doing that, we're going to introduce a new algorithm, is actually become a closed loop learning, whatever, okay? Okay, so here I'm going to give some, for this analysis, I need some more sophisticated model, we call it stochastic, okay? Basically, RG, AG are generated IID from some distribution, okay? RG, AG, each entry are bounded, that seems reasonable. The conditional distribution give A and R, which is the reward, okay, the bits, information, the objective coefficient have a density functions. Then we also assume AAT, expected, is going to be positive definite, okay? And you take, and so basically guarantees that the dual objective function is strictly convex. So optimal dual price is unique. We also assume that BI is proportional to n. So because we are analyzing a large number of n, we want our inventory to be proportional to n. Okay, so there was some kind of a fixed rate di bi equal to n times di. We are thinking about in the reality, the inventory can be refilled if n become large, whatever. Okay, you can think about this. We receive some kind of linear rate. Of course, we assume n greater than m. M is the number of goods, and n is the number of the betas. So again, we only allow DIs. So the fill rate, okay, as a priority, but does not the distribution P. Although it come from IIT, we don't know what's a P, okay, some of those distribution. Okay. We also don't require the constraint of coefficient A to be a density function, to have a density functions, and it could be either 0 or 1 or those kind of things. Okay. Serious about that, again, I'm just let's say for any realization, we denote the offline objective value, Rn star. Then with any online policies, I compute this objective value. So what's the regret? Is the delta n with vector to distribution, take expected Rn star. So this is the offline optimization minus Rn. So we just take that difference, whatever. So this number should be always greater equal to 0. Yes?
So to get the competitive ratio result, you did not need to make any of these IID assumptions.
No, we just,
yeah. Regret.
That's right. Regret will make IID, which is stronger conditions.
Yes.
Okay. Actually, we have some example based on only permutation, the price may not convergence. It's like one reverse over there, over there, you have zigzag because the price may not be unique, actually. Yeah. So to price, yeah, here we're under stronger assumptions, but we don't know the distribution. Thanks. Good question. Yeah. So the expected is taken, but we still analyze the worst regret, which is the super for all the possible distribution. So in the early result, we should be true for any given realization data, but here is for any possible distribution. Okay? Okay. So we basically want to build a bound on n. So here, for any given n, we compute this difference. Then we see as n decrease, how this error would be increased. Increase as n, increase as square root n, or increase as a log n, whatever. So this is our idea to analyze this. So thanks for the question. Yes, all the days for competitive ratio, most of this paper inventory is fixed. We only run this come from permutation, and the market is single-sided, and the objective is analyze competitive ratio. But this one, we have a linear growth, we have IID columns, double-sided regret. Our objective value could be very, very tiny, right? Because somebody buys, somebody sells, and but overall, we assume the trend is selling on the majority side, okay? So the objective, but here we analyze the regret. It's not competitive, it's not a ratio, it's the absolute difference, whatever, okay? If we use that arguments, the previous analysis, we typically give a bound which is O(n), probably small number times n. Okay. Now, give that assumptions. We have a stronger assumption now. So I just want to see how to prove the price convergence theorems. So typical relations, we actually look at the dual of the problems, okay, to see how the data revealed. For that online programming, if you have a data revealed, so this is the BI times PI, so that's the right-hand side, right? Then we have like a YI, which is sum. So this AIJ times PI sum over M plus YJ greater equal to RJ. YJ and should be greater. So basically say YJ has to be greater than 0. So you only the X is positive only if this guy is greater than these guys, whatever. Okay, so that you just write down the linear programming problems. Okay, so in fact, this is undersolved. M typically fixed. If you assume N is increased, and then you have the right. It's just a pure linear program. I'm just rewrite this linear programming by eliminate variable YJ. So what's the Yj? You can prove Yj is basically equal to the positive side of these functions. So if this y is positive, Yj is that positive quantity. Otherwise, Yj equal to 0, correct? Okay? So this is a kind of the positive part function. I heard that in the deep learning, people call this ReLU or something, operate or something, whatever. Okay? So this is basically, this is a dual problem we want to learn. Okay? We want to solve for any given. So pi greater equal to 0. We need pi to be greater equal to 0. Okay? So then let's call this the LNP. This is our linear programming. Then what we did is we divide by n. So this, you divide by n, so this become average level. So this is the average of these root functions. Then you have di, because the bi equal to di times pi. So this is the ratio, okay, we'll talk about. So this becomes these problems. Then you can further think about this stochastic problems, which is, what's this? This is just a sample range, sample average of that one. So what's this problem? This constrained stochastic programming is the infinite version of these problems. Okay? So when you compute this one, you basically want to compute, you basically put a learning called loss function, so you want to minimize this subject to p greater equal to 0. Okay? So it's the sample averages. Okay? Then you expect, as n increase, this solution, the optimal solution p of this converges to optimal solution p of this. Okay? The question is the convergence, what kind of rate? Okay? So here's the theorems. Okay? Exists a constant c such that Pn star. So Pn star is the optimal solution of this. P star is the optimal solution of this. And the square less than c times m log n divided by n. So this is the L2 error expected. Okay? The proof basically utilized nice identity and followed by very careful analysis, the first and second order term in the function bound. Okay? And also make assumption because the strictly convexity, so optimal value convergence to optimal solution also converges. So is this, okay? So my student come out with this proof, and they said, he told me L2 estimate error is not typical in objective Manin statistic. It's stronger than other claims such as the generalization error bound. And however, for our analysis, because we eventually wanted to analyze the revenues, so it's necessary in the content regret analysis for online and kind of learning optimization, which we'll discuss a little bit later. Okay. Okay, so this of course this is not come completely from blue. There was many analyses existing the solution convergence, not just the value convergence for unconstrained. Okay, the quantile regression, you can easily do this, and also sample average approximation and the Huber, Shapiro, they only proved this kind of central limit type of theorems, but our result actually is stronger because our result using Markov inequality implies this kind of result, but this to us, this is not enough, so we still want this kind of a bound, okay? Yeah. And also, our proof is on the weak assumption on some kind of constraint learning. It's not most learning which is assumed is unconstrained, but here we have to assume p greater equal to 0, which become usually you have a constraint, the function become non-smooth. Okay. Now let's just recap. So Pn star is the offline dual optimal solution, but it's the computation requires the full knowledge. Okay. If we observe the first T column and the corresponding coefficient of objective value, then we can compute the PT star based on reviewed data and that proportion resource. Okay? Because the dual convergence theorem, we know PT star and the Pn star should be close because T is getting close to M. Okay? So this is require only knowledge of first T realization observation. So this is we could apply this online learnings, whatever, on the fly. So this is a very perfect fit. So basically, we build the connection becomes, original problem become a decision problem, but the later problem, the dual problem, become a learning problems. So it's like we alternate this. We use primal problem as a decision, and then we use the learning on the dual side. Okay, I believe many online optimization or decision problem, it turned out must be related to some kind of a dual problems, which become a learning problems. How fast you can learn the price or Lagrange multipliers. Okay, so this is this. Keep in your mind, was open. We don't know whether dual convergence, and also this theorem hold for is RGA is positive or negative. Okay, AIJ. So they become a true linear program. Now I'm going to bound regret. Okay, first here we just build the upper bound. Okay, so we basically take expected value, take expected value, we can take a vector value, become an infinite horizon. Okay, so we basically use this as RL as our benchmark. So this is upper bound, okay? Is the our objective. So in this case, what we do is we have a thermal theorem RL because in the regret bound we have to compute for R star given the n samples, okay? Given n realizations. So this number, this RL is like n stochastic versions, and P star also over there. Okay, so of course, when we analyze, instead compared to expect the R star n, we use RL. So because this is upper bound, use deterministic optimization as a benchmark in the regret analysis, and has been used in several people, and most in the operation management or revenue management literature, which comes from people in the operation research. Okay. Now the question becomes what? Because this is a constrained learning, or in the primal problem they have a constraints. So we really don't want the constraint to be violated. Okay. So the key analysis now is to build this remaining resource process as the stochastic process. What's the stochastic process? BT. At the very beginning, no sale occurred, so our inventory just equal to beginning. But BT equal to BT minus 1, the remaining inventory at the end of last period minus the decision you make at the current period. Okay? It's the inventory runs down, okay? Because so this becomes a stochastic process. In particular, at the end of N, this is the corresponding remaining resources at the end of the entire sale horizon. We don't want, especially for those constraints which are bending, we don't want this have too much left. So this is actually, the constraint online optimization is hard because we have to obey the constraints. You don't want to sell to running out of inventory too early. You also don't want to have leftover and stuff. So this process become a kind of a stochastic process. Okay. Of course, each of these depend on pertains and to certain online algorithms, which you can also call the policy. Okay. So here's the something which we defined is the process. The whole cell will be stopped if your inventory running below certain threshold. Here we put it as 1. Okay, because once you have inventory below 1. Each time, some people wanted to buy one, although the shadow price permit you to sell, but actually you cannot sell because you are running out of stock, whatever. So this kind of a stopping time, okay? You want this time to be very close to N, whatever, which is right at the last customer, you're running out of inventory, okay? So this is something, we want this, and this is also true for any of these, okay? So here's my little bit of theorems. Again, we want this is our regret. We use RL, which is upper bound on this. It turned out to be less than some constant times expected value of this. What's this? This is any price you adapted at the Tth period used in the decision rule. This is the stochastic optimum ones. So you sum it up, n minus 5. So this, you want this to be very close to n, but at least n plus and minus log n or something like that. What's this? This is leftover kind of stocks, leftover unsold items. Okay, so in this case, it's the 3 error. What's the quality of the price you lend? PT should be close to P star, or you want this running out of stock time very close to n. Your stock can maintain until the whole horizon. Also, you don't want to left over, okay? So 3 type of error. So represent, you want to do this, which is makes sense, okay? So for example, you say, I have a PT equal to P star. That's not a good policy? Not necessarily, because use PT equal to P star, this number could be very high because this is a stochastic process, okay? So anyway, so otherwise the Lagrangian, that's why we use the upload L. So this is a leftover inventories, and basically use the Lagrangian, which seems new in the analysis, and also used some tricks to analyze probability and G and G star. Okay, okay. So yes. These theorems turn out to be very useful. It's applied to many constrained online optimizations. So basically say whether the due price accurate it is, and how much constraint the last 2 items basically how much violation of the constraints. Whatever. Okay. So many literature that imply many people started this problem with online learning, but our theorem looks like it's like a unified, analyze all these error bound or quantity bound. So let me now take a look. Okay, finally, yeah. So I'm talking about this closed loop solution. So what's the meta version of algorithm in literature? So basically, compute the due price vector PT plus 1 based on the observation of these previous ones. Okay. Then we compute this price, we set this decision rule, and also we have to check the constraint. If constraint is violated, then this rule tell us equal to 1, but we cannot equal to 1 anymore. Okay, so this is kind of a stopping kind of a time. Okay, so common feature of all the previous online algorithms, they decide PTS1 is basically use the review data. Okay, and ignores the past action already taken. So this is like an open loop learning. Essentially, all those algorithms are aiming to estimate the P star on our stochastic models. Okay, this is ground truth P star. But however, chasing P star, which we usually call in Markov decision called the stationary price, that's when the horizon is infinite, may not be a good strategy and may not be adaptive enough. Okay? Because we really want to learn Pn star is based on a particular realization of the data. Okay? And this itself is the moving target, is the rundown level. Okay? So we need a closed loop learning. We need to develop a non-stationary policy, whatever, which is on finite horizons when it's fixed. Okay? So this is the problems. Okay? So I'm just giving you an idea what it used to do. So you can see in the periods, we just based on some time point. So this is the T number of customer reviewed, T number of customer. Then we give them T times DI. Remember, what's the DI? Is the BI is the DI times N. So we give that a proportional DI. DI is like a resource per customer. Okay, okay. So this is the T times DI. We solve this problem. Nothing happens when AIJ is over there. Okay, we didn't adjust the DI. We just use this kind of like a fixed one. So this is our, which we call the open loop. So now we develop another one, which is called the closed loop. What is the closed loop? So suppose T data is already reviewed. At the end of T's period, how many inventory we have? Remember PIT, which is stochastic process. Okay? how many customers remaining in the pool is n minus t. Then that remaining inventory allocate average over n minus t. That's the new rate. It's not going to be di anymore. Okay, here we just use di, which is the ground kind of. So what we really want is we should recompute a shadow price for these remaining resource problems. So it's like you have things, if you made a mistake, basically already made, now you stand as new problems based on remaining inventory. Okay? So this one, which means the right-hand side, is also updated based on the decision you already made. Okay? So this is what we call so it's like a decision already made, feedback into new right-hand side. So each time we chase that moving, okay, we start with the new problem with a smaller number of customers, with smaller inventories, but more number of samples. Okay, so in this case, we accelerate this kind of learning shows, chase that idea. Okay. This is called algorithm. Now I also thought, let's algorithm 3. Okay, let's say this is stationary ground truth P star is given. Okay, give us free to use. Okay, and the P star could not be the case if P star is given free to use. Okay, again, chasing P star may not be good because this is we should chase a non-stationary policy. Okay. So again, we run some simulations. We run the input, Aij is some uniform, Aij equal to 0.5, 1, so this is positive, negative. And then we also generate accordingly, okay, permutation. We just use that worst case example given in the paper Agrava et al. Okay. Actually, I just want to say for these two, they may not satisfy our assumptions. Whatever. Okay. So we run some simulations. So this compilation number of goods, number of customers. A1, A2, A3, we basically, this is the difference between offline values versus online values. Smaller of this number, that means the better learning of these policies. You can see, even give you P star, actually may not be better than the closed loop learning. Okay? So this one, yeah, especially for something. And so again, this is algorithm 1, which is dynamic learning, but it's the chasing P star. So this is adaptive learning, or called closed loop learning, or this is giving you P star, that you're free to use. Okay, so you can see adaptive is much, much better, or closed loop is much, much better. Yeah, sure. Yeah, I'm done. So this is this is the blue ones, which is log n, looks like log n, and this is too much token like square root. That's for random input. This actually looks like a linear, but however, adaptive looks like a constant. Okay, actually, what we went on is based on observation. We can prove, okay, for each of the 3 algorithms or policies, A1 actually it is like a square root n. So our algorithms, adaptive closed loop algorithm, is like log square n. And this one is a square root n. Even give you P star, you still have a square root n. Okay. So basically proved by careful convergence. Okay. So here's the summary. We basically resolved 2 open questions under these stronger statistical assumptions. Convergence result on the dual problems. So Rj, Aj be general, both positive and negative. So this would be a true LP. We also provide a generic framework for online convex representation, which is on the decision side, and we classify it as a dual learning kind of a process, okay, which is especially with constraints. This would work in general for regret analysis, many problems with current decision and primal and learning on the dual. Okay. Then we derive regret bounds in the large N regime. Okay, forced regret is OLP to the best of our knowledge. Online, most people use competitive ratio. Okay, so we basically use regret. I'm particularly interested in develop new adaptive and closed loop learning OLP algorithms with a proof of bound which is log square n. So in most statistical problems, you probably see square root n or n something. Okay. with some unconstrained, you see some log n, but however. Then I leave just more open questions, but on the simulation, looks like should be log n, okay, instead log square n. But also, especially on the random input 2, looks like our algorithm actually is a constant. So I just leave a little bit open questions, and then that's my talk. Thank you. Yeah.
A couple of questions when Andy sets up.
Yes.
Actually, about the algorithms used, let's say the hacking problem in the beginning.
Yeah.
You need to solve a whole linear program at every iteration to update.
Yeah, this is another issue. Actually, many people don't need to solve that linear programming, start from anew. They can use the previous done, use the iterative process to update the linear programming because all the previous algorithm is already given, especially DI is fixed. So yes, but I view that's a different, it's more how to solve that linear programming efficiently. Yeah, many people, and probably you also have many, especially when you have first order algorithms, they usually use the warm start and then start a few iterative process to update the solution. That's right. Okay, that's good. Okay, sure. Okay.
Let's thank Yini again.
Oh, okay.